Class is now starting. All attendees are in listen-only mode.
Hello and welcome to today's webinar, National Electrical Code, On-Site Power Generation and Distribution Part 1. My name is Cody and I will be your moderator today. This webinar will last for 3 hours and 15 minutes and we do have some notes to cover before we begin. Please be sure to be logged on to the webinar through your own individual connection so that we can accurately prove attendance in the event that you or Half Moon Education are audited. We require individual connections so that you can access the quiz at the end of the webinar. The quiz will automatically appear on your screen after I end the webinar. If you are unable to successfully submit the quiz, you can access the quiz via the thank you or follow-up email that is sent about an hour after the webinar has ended. Certificates will be issued for today's webinar. If you did not successfully submit the quiz after attending the webinar, please be sure to complete the quiz through the thank you or follow-up email. The certificates will be sent via email in PDF form, and if you need your certificate sooner, please reply back to any emails you have received regarding these seminars or call into our office. We will be taking questions throughout today's webinar. If you have any questions, you can ask them in the questions area of the GoToWebinar panel. And with that, I'll hand it over to our speaker today, Mr. John Ross Cromer. Mr. Cromer is a master electrician with a mechanical engineering degree from the University of Pennsylvania, a NAB CEP certified PV installer, and author of Solar Power Design and Development, An Introduction to Rooftop Solar. Take it away, JR.
All right. Hey, everyone. Welcome to this program. If you're like me, you started out as an engineer and I didn't know much about electricity even by the time I got into solar power. I had taken some, circuitry classes in college, but other than just brute memorization, didn't really have an appreciation for like what's the difference between a volt and an amp. I got into solar after working a few years in the oil industry, mainly because I felt the construction scope would be easier to kind of manage and execute than other construction scopes that that I was currently being tasked with. And so only through just working and doing design and doing installation have I developed enough knowledge and appreciation for National Electric Code and kind of understanding the philosophies behind it rather than trying to memorize code via brute force. National Electric Code is rational. It's a safety code. It's trying to establish the bare minimum threshold of safety. And as you get more into code, you can find kind of some shortcomings and also some areas where code is being reasonable rather than unreasonable. And so I kind of wrote this class to better introduce engineering managers to the nuances of designing and installing renewable energy systems with respect to National Electric Code. Hopefully many of you, are just trying to broaden your understanding of code, and maybe you haven't flipped through National Electric Code. So what we're going to try and do today is kind of guide you through National Electric Code from start to finish, so that you can better understand the nuts and bolts and brass tacks of renewable energy systems. Code is very expansive, and just the first few sections of code comprise most of code. And so I would say sections 200 and 300 kind of outline electricity safety fundamentals. And then often by the time you get into the specialty equipment sections towards the end, you'll find that the code it really kind of begins to repeat itself, almost like petals on a rose following a pattern. You'll be reading sections later on in code and being like, hey, I thought we covered that before. Because mainly by the time you get to the specialty equipment, they're kind of recalling or just expanding upon the rules that are defined in the earlier sections. So, if you're like me, when you got into solar, you're just reading the solar section 690 and trying to figure out what all the rules are. And that's really going to, kind of, you'll get your shoelaces tied together if that's as far as code into code as you get. Now, if you have an engineering degree and you learn a little bit about National Electric Code, like myself, uh, being that we're in a continuing education environment for architects and engineers, you're probably better than the average test taker. And so the way, my path to becoming a master electrician was a little non-traditional. I came about it through with my engineering degree and some knowledge of code. I was able to go and pass my master electrician exam and become a master electrician. Now, that still didn't mean I knew the nuances of conduit and cables and fittings. And that only came with field experience. So we're going to be getting into some of those nuances in class throughout the next 2 days. All right. So kind of one good starting point for National Electric Code is to understand it's not like a governmental code. The NEC standards are copyrighted by a private organization, and that organization maintains its operating funds to support code through things like selling code books, etc. And governmental entities will adopt National Electric Code as their standard. And so it's not a governmental code where you can go online and just print out a copy of it. You might balk at the cost of actually buying a code book and say, well, hey, if I have to design to code, why isn't this stuff freely available? And the reason is, well, it's not, it's not a publicly owned asset. It's maintained by a private organization. And so what that means is that when you refer to code, the kind of rule of thumb is that you should refer to code by reference only, which means, just taking code and printing out sections word for word can get you into a little bit of trouble with the NFPA because that's how they maintain it. And so when you get on true, say, electrician discussion boards, you may be frustrated by the fact that electricians are referring to a section of code and they're citing the title and the number, but they're not spitting out the text. And the reason is they're being professional and they're saying, okay, as tradesmen, if you're doing electrical work, you should go buy a copy of code, and we should only refer to code by reference only. Now that makes teaching a code class kind of hard to do if you can't just print out copies of code and distribute them. And so if you're frustrated a little bit by the course slides not being 100% complete, that's kind of why I'm trying to bridge the gap between providing enough text to make the class worthwhile without giving you a complete manual that you can use in lieu of going out and buying your own code book on your own. Now that said, Google is a very big place, and you can usually find texts or at least partial text of code with enough searching online. Um, if you are interested in taking a path towards gaining a master electrician license, which is useful if you're interested in starting an electrical contracting firm, you want to have a code book anyway because the master electrician exam is open book. And so, once you get familiar with start to finish code, you can use it to improve your own credentials in your career. So code is kind of unrolls starting out with the basics. So the very first sections are things like definitions and installation requirements. Just as an example, let's start out where it gives us the definition of deteriorating agents. No conductors or equipment shall be located in damp or wet locations or exposed to gases or excessive temperatures unless that equipment or nuts and bolts and parts, conductors, are identified for that purpose. And that's particularly important with solar because a rooftop is an extreme temperature. And so you can't just go buy any cable at Home Depot or Lowe's or Menards and put it on the rooftop. The cables for solar power that come out of the solar panel, that come out of the back of it, are not inside conduit. You'll transition into conduit, but they're rated for being in high temperature environments and wet environments because a rooftop is a wet environment. And some batteries, like flooded lead acid batteries, which really have the best value for the off-grid market, they'll produce gas that has deteriorating corrosive effects to it. And so, in solar, we're dealing with wet conditions, we're dealing with high temperatures, we're dealing with gases. And so, not all the parts that you'll just find at your, big box home improvement store are going to be suitable to use on a solar job site. You might have a disconnect switch that's only rated for a lower temperature environment, or a junction box that's only rated for a lower temperature environment. You might find that when we get into how we calculate temperature correction, a common one is a lot of solar specialty equipment is rated for higher temperatures, and so you don't have to do as much oversizing of your conductors because they're given that higher temperature rating versus a more generic device would have a lower temperature rating. The definition of a damp location versus a wet location comes into play in solar. A damp location is something that is not saturated with water, so that's not going to be exposed to rain or a sprinkler system. Whereas a wet location is more like, being outside, exposed and unprotected. So, if you're underneath like the eave of a house, or like a covered garage or a porch, that would be a damp condition as opposed to a wet condition. And as we get into our cable discussion, there's one, particularly for residential design, there's one particular cable that I like to use for my internal conduit runs, and it's given a damp condition rating rather than a wet condition rating. And so depending on the attic space, I'll run wet condition conduit up into the attic and then transition into damp, or I'll just tuck a very short section of this damp condition cable out of the soffit of the rooftop, but only by a couple of inches so that I could claim during inspection that that damp rated cable is being protected by the overhang of the soffit. And then I'll just mount a junction box, 6 inches below the soffit in order to transition into my truly wet rated conduit, such as EMT conduit. Just one, one kind of issue that I'm dealing with on this commercial job site is we use a lot of EMT conduit, and EMT conduit is commonly connected through these kinds of compression coupling. So when you see this is a compression coupling, this is a compression coupling, this is a compression coupling, and this one is a little bit different of a compression coupling. And what we see is it has this rain tight label. And so let me see if I can't get a couple more look at the insides. The main difference between this this rain tight compression coupling versus something that is not rain tight is that inside this compression coupling is a few more parts than what you get inside a traditional coupling or connector. And so here we have like a neoprene washer that provides a little bit more of a seal to it. And then I'm not seeing any photos for the insides, but the main difference is inside these rain tight compression couplings as opposed to non-rain tight compression couplings is on the inside you get an additional little metal ring and plastic ring that makes it a little bit tougher to fit together than a coupling that doesn't have it, but it gives it a little bit more water resistance than a traditional coupling. And so just things like knowing your locations, and if you're in a wet environment, making sure that your conductors are rated for a wet environment, making sure that your fittings are rated for a wet environment is important, and that can kind of trip you up because usually at say your box stores or even your electrical distributors, they're not going to be stocking the rain tight couplings as opposed to your traditional couplings. So you have to add a couple of days lead time to kind of get some of the more specialty pieces of equipment. We're dealing with a couple of different locations when we're doing energy systems. Basements are considered to be damp environments as opposed to the roof, which would be a wet environment. Inside the attic is considered to be a dry environment. And so you can get away with different conductors inside the roof as opposed to outside the roof. As we further explore our cable selection, what we'll find is that, when you have an outside of conduit conductor rated for a wet environment in extreme temperature, not only is it going to cost more money than something that's in a dry condition conductor, but it's also because it's going to have a thicker cable jacket. That thicker cable jacket will give it more sunlight resistance and water resistance. Well, we don't necessarily want to put a conductor that's rated to go outside of conduit with a big, thick insulating jacket. We don't necessarily want to put that conductor inside of conduit where it's going to be cramped around other, cables wearing big, thick, heavy coats and taking up a lot of space and generating a lot of heat. And so, it can be a good idea to transition your cable types when you get into the interior of a building versus the exterior of the building. And I'll generally make that call dependent upon how long a distance we have to go. But the general consensus is, if even though, say, where we're transitioning into the rooftop right here, even though the inside of this conduit from this point is a dry location, the a very a very fastidious inspector might say, well, hold on, if this metal conduit is just sticking up through the rooftop, then the other end of this conduit is going to be in a wet condition, and if that end of the conduit is sticking up in a wet condition, then you need to make sure that the conductors used inside of this conduit are at least rated for a wet environment. Temperature is a major consideration when dealing with rooftops. What 110.14c is saying is the temperature rating associated with the ampacity of a conductor shall not exceed the lowest temperature rating of any connector, termination, conductor, or device. And so what that says, if you're using, say, 90C cable, and you are landing it on a box that has a 75C Celsius temperature rating, you need to make sure that you're doing your temperature corrections calculations at 75C instead of 90C. And so it's always a good idea when you're buying your disconnects and even your inverters, an inside inverter versus an outside inverter may have a different temperature rating on those terminals. What the worst thing to do is to do all your electrical calculations using your high temperature rated conductors and then land them on a terminal block that has a lower temperature rating, and then not do the calculation to make sure that you're still in the clear. What will happen if you skip over that is you might find that terminal block you've landed onto is heating up and starting a fire if your conductors are not are just right sized for that higher temperature rating, and all of a sudden you've dropped down to a component that has a lower temperature rating, and you've moved on to the other side of your minimum safety threshold. And so to kind of put a picture to it, here's our solar cable, and we can see that it has a 90C temperature rating. And here's a solar specialty box with these terminals, and these terminals generally with solar are going to stick to this 90C temperature rating. But if you're trying to just use a generic box and generic fuse holders that you might find in your box store, more than likely they're not designed with solar in mind, and they may have a 75C temperature rating, at which point you need to do your calculations at 75C to make sure you don't exceed the temperature rating of that terminal block. So what am I talking about with temperature correction factors? So here we have a chart that says ampacities for conductors rated up to 2,000 volts with ambient temperature correction factors, based on 86 degrees Fahrenheit. And so what you'll have in code is a chart that will say, okay, here's all the ampacities of various conductors based on 86 degrees Fahrenheit. And you might say, okay, well, that's fine, but on a rooftop, I get much hotter than 86 degrees Fahrenheit. And furthermore, I might have a selection of cable. I might have, regular, cable that's rated at 75C, or I might have solar cable that's given a higher temperature rating because it has more insulation, rated at 90C. Or I might be trying to use, some spare cable that's cheap and not really solar cable, that has a lower temperature rating. And so what we see, and then I have, the fact that not only do my cable jackets have different temperature ratings, but it might not actually be 86 Fahrenheit outside. Up on that rooftop, it might be, 120 or even more. And so if all of my ampacities in my code book are calculated at 86 degrees Fahrenheit, how do I find out what the ampacity rating is going to be if it's at 120 degrees up on the rooftop? And so National Electric Code will, instead of making you actually crunch the numbers, which is probably what an engineer is want to do, National Electric Code is not written for engineers. It's written for electricians, and it's not trying to pinpoint, what is the down to 3 significant figures, the turning point between a safe wire and an unsafe wire. Instead, National Electric Code is trying to provide a guide for that electrician to say, use this wire and you'll be okay. And so all of these charts in code are really just kind of like a slide rule or a fudge factor or a cheat sheet to allow the electrician to pick out the appropriately rated wire without actually crunching the number. So it says, okay, we're going to do all of our ampacities based on 86 degrees Fahrenheit. But if you're operating in an environment that's rated for 120 degrees Fahrenheit, then you need to discount the ampacity by a certain amount. And so if I'm using the chart that tells me the ampacity rating of my cable, and I look in the title of the chart and it says the ampacities of these cables are assuming 86 degree Fahrenheit operating environment, but I'm actually in a 125 degree operating environment, then what that means is I'm at an elevated temperature, and that means the ampacity of my conductor needs to be derated. And so if I've done all of my calculations based on an 86 degree Fahrenheit temperature, and why would we do that instead of just starting out at the exact maximum design threshold? Well, it's because National Electric Code is providing us like workarounds from actually calculating the numbers. So they give us charts with all the ampacities for all the different cables, and then they say, and this chart is based off this particular temperature, and when you deviate from this particular temperature, we're going to give you a different chart that'll tell you the discount factor for that deviation. And so to go from 86 degrees, but I'm actually up on the roof at 120 degrees, I'm going to have to discount that ampacity. And based on if I use a cable that's only rated for a low temperature environment, that discount factor is going to be substantially greater. I'm going to have to knock more off than if I'm using a conductor that's rated for that high temperature environment. And so we see, this chart that says, okay, for high temperature cable versus low temperature cable, you don't have to discount as much off of the rating of the cable because the cable is rated for higher temperatures. So it can withstand higher temperatures, and so you don't have to derate it as much as you would with a lower temperature. And then we also see on the other axis the reality that says, okay, but if I'm doing all my calculations at 86 degrees and I'm slightly above 86 degrees, but I'm using a high temperature cable, I don't have to discount the ampacity of that cable very much. But if I'm actually operating in an ambient of 120, I see that discount factor uptick. And so that begs the question, well, how hot does it get on a rooftop? And there is a resource out there that we use in solar all the time to calculate solar production. And so we can also use this resource to tell you what your rooftop temperatures are. And so that resource is called PV Watts. I'm going to pull it up and do an example. But while PV Watts is a very quick and easy tool for determining how much production your solar array will produce a year, there's a wealth of environmental data that can be gleaned from PV Watts if you go all the way through to the end with your calculation and actually go and download the hourly performance data from PV Watts. And so you go through the PV Watts calculation and you download the hourly performance data, and you actually get a printout of every single hour of the entire year with what power output the system is expected. And I have to apologize for a minute. I'm on site today doing this webcast going off of my mobile hotspot. So if the audio degrades, it's probably because I'm getting a phone call on my phone. And so I'll just be kind of ignoring those phone calls as they come in, and the signal should catch back up. And so what PV Watts will do is give you a printout of for every hour of the day what the system output is going to be, and that's very useful, not just for solar performance estimating, but for what time of day it is, which then can be cross-referenced against what time of day your solar array is shaded, so that you can perform shade loss calculations. In my battery classes, we'll take the PV Watts output and we'll take the building consumption and we'll subtract the two. And that'll be a building block for how large of a battery do we need to take the system off grid or to do some peak load reductions. But there's one particular column that I want to call out, which is cell temperature, which is pretty much akin to what the temperature of the material on your rooftop is going to be at. And so this is all done in Celsius, but what we see is on a 12 degrees Celsius day, our cell temperature is getting up to 24 degrees Celsius, which is without knowing exactly what these two numbers, how they compare to Fahrenheit. I'd say, 24 is going to be a lot more than 12. And so let's do some conversions. I ran a PV Watts calculation for Phoenix, Arizona. And again, how you would do that is just go into Google and you Google PV Watts. I'll go ahead and put the link in the chat box so you can do it on your own if you want. But here we are. We're just going to put it in Phoenix, Arizona. I probably should spell Phoenix correctly. And so here we are in Phoenix, Arizona. And I like to do a PV Watts calculation just for a 1 kilowatt solar array, because that gives me a scalar that I can do to a 10 kilowatt solar array will produce 10 times as much as a 1 kilowatt 5 kilowatt will do 5 times as much as a 1 kilowatt. So I always like to think in terms of what will 1 kilowatt of solar will do. I'm not going to mess around with PV watts too much. But what we see is in Phoenix, Arizona, 1 kilowatt of solar will produce 1,677 kilowatt hours a year. I like to just mentally think, okay, 1 to 1.67, that's just slightly less than 1 watt producing 1.7 kilowatt hours a year in Phoenix, Arizona. Now, the national average, that ratio of 1 to 1.4, 1 to 1.7, and in most places it's 1 to 1.3 or 1 to 1.4. But if I know what 1 watt will produce in terms of kilowatt hours, this was for 1,000 watts and we're producing 1,677 kilowatt hours. If I can just remember 1 watt will produce in Phoenix, Arizona, 1.7 kilowatt hours, and I'm a solar installer in Phoenix, Arizona, and someone calls and they say, oh, I want a 5 kilowatt system. I'm thinking, okay, 5 times 1.7, that solar array will produce about 8,700 kilowatt hours a year. If electricity is 10 cents a kilowatt hour, that solar array will save about $870 a year. So if you know this PV watts ratio of 1 watt to how much production, you can start performing off-the-cuff performance estimates right in front of your client, and it'll make you sound like you really know a heck of a lot about solar production in your area. Well, really what I just wanted to show you is here you can go in and download the results, and it'll spit it into an Excel file that you can just start playing around with a little bit more. And so if I want to know what my maximum temperature is going to be for the solar panels up on my rooftop, I download this hourly data. I'm going to open up Excel. And I say, okay, I'm going to look at my, here is ambient temperature. And here is, actually there's ambient temperature and then there's cell temperature. And so if we're basing it off ambient temperature, I'm looking through every single hour of the year, and the maximum temperature is 46 degrees. And then just for grins, our actual cell on our actual panel is getting up to 83 or 84 degrees. And so depending on the calculations and code are based on ambient. And so actually they've updated the temperature condition, and we're actually seeing even higher operating conditions from here. 83 degrees would be that the cell temperature is getting up to 170 or more during the hottest day of the year in Phoenix, Arizona. And so it's always important when you're doing solar to make sure you're looking at this, this highest, using the high temperature ratings. Dedicated equipment space. This is another very common code violation. I'm looking at my current job site, and up on the rooftop we have gas lines, and we also have electrical equipment. Electrical equipment requires dedicated space. You can't combine, your plumbing space with your electrical space with your gas space. They have to be separated. Local jurisdictions, other parts of maybe not National Electric Code, but other parts of building code will say, oh, you can't have your electrical to be within 2 feet of that gas meter going that's taking the gas into the side of your building. You might say, well, that's not part of National Electric Code. Well, there still are other parts of code that govern building design. And so the first part is your electrical space cannot combine with plumbing or gas or HVAC. Now this is Half Moon's electrical room. And immediately you might say, well, hold on, here's a water tank, the water line, and here's my electric service panel. So is this a code violation or not? And it depends. There are rules that govern the immediate space that your electrical equipment is located in, but the space that's right next to it may not be in this dedicated zone. And so there's rules that govern, what is the size of this dedicated zone. Let's take a look. So we're talking about height, we're talking about width, we're talking about depth. And the way that I like to think about it is, what is the space that you would need to comfortably stand in front of this electric service panel and work in that electric service panel without conflicting with other scope? And so there's a couple of different rules for what that space is, regarding the depth of the space. It might be, well, what's behind you? Is there a wall behind you? Is there other electrical equipment behind you? Or is there nothing behind you? Are you in a big open gymnasium and that service panel is on the wall and there's a hell of a lot of space behind you? That depth of working space is going to range between 3 and 4 feet. On that 3 and 4 feet, if there's nothing behind you, that's dedicated space will be, 3 feet. If there's another piece of electrical equipment behind you, that dedicated space needs to be 4 feet. If there's a wall behind you, that dedicated space needs to be 3.5 feet. And so that's, there's code for that. The width of the working space is the minimum of 30 inches or the width of the equipment. And what's interesting about the width of the equipment is, like on this piece of equipment, you can say, okay, well, there's only, a couple of inches between that and the doorway. Well, here's your 30 inches of space for this panel, and then here is your 30 inches of space for this panel. And so actually your eligible space is going to go from the edge of this panel to the edge of that panel, provided that this dimension, that we just drew out here is greater than 30 inches. So again, that's, you think about the width of a human and say, okay, well, that human being needs to be able to stand comfortably in front of this equipment and work on it. And so they need to have, this side of the room may be up against the wall, this side of the room may be up against your water heater, but there needs to be at least 30 inches of working space in front of the equipment. Even if the guy's standing off a little to the left or a little to the right, there needs to be at least 30 inches for someone to work there without getting in conflict with other scope. the height of the working space is the minimum of 6.5 feet or the height of the equipment. And so this one gets a little bit trickier because it's like, okay, well, what if I had a water line and this water line wanted to run over, this way and go underneath the panel? Well, that would be a code violation, unless I had a little bit of a platform here that I could stand on and work on. The code is you need 6.5 feet of working space tall. So again, you think about the height of a human, maybe 6 feet. Some people are a little taller than that. Some people are shorter than that. Well, they're trying to say, okay, well, we need at least 6.5 feet of working space from the floor up to the ceiling. And so, it might be that you have a stairwell. You want to say, okay, well, underneath the stairwell is a perfect spot for me to land my solar inverter or my box. You need to make sure that you have 6.5 feet of working space for that. Otherwise, it would be a code violation. You might say, okay, I want to put all of my equipment outside. And so I want to build like a storage shed and put all of my equipment inside the storage shed. Or the other alternative is you could have a box with a hinged lid. And so the difference being, do you service the equipment by walking inside the storage shed, or do you stay outside and kind of work by opening up the box? Well, if you go with the storage shed option or the alcove option, technically you need 6.5 feet of working space in front of whatever electrical equipment you need to work in front of. And so there are depth requirements, width requirements, height requirements. And then another requirement that's a little bit trickier, and come back to this. The other requirement that's a little bit trickier is another depth requirement, which is how far can one piece of equipment overhang another piece? And so in this case, we're showing, let's assume we have a battery and we have all this wall space. And so we want to butt up the battery against the wall here, and we want to butt up our solar equipment against this other wall. And so you're like hanging your solar boxes along the wall, and you run out of space, and you're like, oh, okay, well, it's still all dedicated equipment space. So can I just put my box above my batteries, and my batteries are going to stick out relative to the depth of the box? And the rule is you can only kind of overlap your equipment like that if they're all within 6 inches of each other. And the mindset being, okay, well, if these lead acid batteries are pretty large, and so if I have a battery that's, say, 36 inches long, and I have a box that's only 12 inches long, the problem is if I want to work in that box and the batteries are protruding by 24 inches, now I'm having to lean over the battery rather substantially in order to access that box. And so code says, no, you can't do that. That's a safety hazard. The depth of the working space can only be up to a 6-inch overlap. Anything more than that, you would be leaning over electrical equipment in order to service other electrical equipment and that's a potential safety hazard. And so this is kind of interesting where here's a well-sized storage room for an off-grid house. It's about 15 feet by 20 feet. So we're thinking, okay, well, can't we just put, everything up against this wall here? Well, we get into the design work. We look at these batteries, and these batteries are over 3 feet long by about 10 feet wide. And there's other things that we talk about in our battery class about strengths and weaknesses of lead acid. And a big weakness is that they're very, very heavy. They're also big. On a separate note, these batteries right here are lead acid, but they're tilted on their side. These are sealed lead acid, and you don't need to service sealed batteries. The Tesla Powerwall is a lithium-ion battery, and it's a sealed battery. You don't have to maintain it. Forklift batteries are unsealed. So forklift batteries will produce gas, and you have to water them to maintain their electrolyte level. Well, why would you ever do an unsealed battery over a sealed battery? Well, it's kind of the same thing as blowing air into a balloon and tying a knot around it versus blowing air into the balloon and letting the air come out, and blowing air into the balloon and letting the air come out. Which is going to last longer? You're going to be able to blow air into that balloon and let the air out, and blow air into the balloon and let the air out for years. Whereas if you blow air into the balloon and tie a knot around it, it's going to lose its original physical state, over a shorter period of time. And so a sealed battery is simply not going to last as long as an unsealed battery of equivalent technology. Therefore, a sealed battery is not going to be as cost effective as an unsealed battery. At the same time, an unsealed battery does require maintenance. And so, it's not like it's much maintenance. Adding water to a battery is easier than doing an oil change on your car. I'm not the kind of guy who wants to do oil changes on my car, but topping off batteries with water once a week is all of a 1 minute task with the right equipment. And unsealed batteries are simply more affordable than sealed batteries within the lead acid class. And so, sometimes it's the money thing where, you want to go and design an off-grid house. Your battery bank is going to be your most expensive option. And the best way to reduce cost on a battery bank is to go with unsealed flooded lead acid. At the same time, what you get in these unsealed flooded lead acid batteries are little servicing holes inside the batteries that you add water into. And these little service holes are dotted throughout the entire battery. And so then it becomes okay, well, I have to access these service holes. I guess they're not well pictured here. But, another design point that we came into is well, if I have these little service holes that are kind of dotted throughout the battery, you can kind of see my problem here, which is if I put the long end of this battery against this wall, now I'm going to have to lean over the battery in order to access that back cell. So, actually, after I made this slide, going back and thinking about it, what we did in this room is said, well, okay, if that becomes a problem, we can put a little window in this wall, cut a hole in the wall effectively to be able to access the back side. But in your battery room layout with an unsealed flooded lead acid battery, the most space effective way to do it would be to say, okay, the short end of the battery is going to go against the wall. And what we know about working space is that up against this wall, there's going to have to be about 3.5 feet of offset between this wall to maintain my working space. And so, kind of what in my off-grid class, what we say is, if you're doing a unsealed flooded lead acid battery, the most space efficient way of putting that battery in a battery room is to take the short end of the battery and offset it from the wall by 3.5 feet, and then take that short end and butt it up against the edge of the wall, and that way you can access all sides of your battery bank for servicing. And another thing about off-grid systems is you're not usually just having one solar array and one inverter. Often you're buying multiple inverters to build in some double redundancy. The last thing you want is for there to be a system failure that takes out your entire system. So it's very common to they call it double stacking or triple stacking your inverter systems. So here we have multiple inverters and multiple charge controllers. Whereas on a batteryless grid-tied system, you usually just have one inverter, and you don't have batteries, you don't have charge controllers, and so a traditional batteryless solar array doesn't take up very much space. But batteries are coming back now into system design as solar policy becomes anti-consumer. When the consumer does not get a good deal for selling back to the grid, more consumers are taking a look at batteries and saying, okay, well, solar costs have come down, and so can I add batteries to my system and not need to sell back to the grid? And that is rarely economic for a residential customer. It can be very economic for a commercial customer. They use their batteries in different ways. When we talk about those features in different classes. But the point is when you're designing a larger system that has solar and batteries and the panel board to connect it all together, you start to get into more and more space requirements. And so if I wanted to, take this, this particular inverter wall and this particular battery and put the long end of the battery against the wall, which in hindsight we wouldn't do. We would rotate this battery bank 90 degrees and have it stick out so that we could access the cell, but then we would still need our 3.5 feet of additional space against the wall. We're looking at at least a 15-foot space requirement for everything to hug the same wall, which is well beyond the size of a typical closet in your garage for your water softener and water tank. We're talking about rooms that are needed for this stuff rather than just a little coat closet that's repurposed for your electrical gear. And so it's kind of funny that, it's a common problem because you don't have a lot of space in your buildings. And so these are pictures that I took off of this particular battery manufacturer's website. And it's like, okay, well, there's not 3.5 feet of space between this wall and this inverter. B, there's really no good way to access the cells back here for maintenance. C, the batteries are sticking out by way more than 6 inches as compared to the service panel. And so it's very easy, without a lack of good design preparation in your battery rooms, to not be able to fit the stuff in a code compliant manner. And so what that might mean is you can't go with the cheapest battery system on the market. You might not be able to go with an unsealed battery that you have to service. You might have to go with a sealed battery. If these were sealed batteries, then this would not be a problem because you wouldn't have to service these cells. So let's talk about the definition between ampacity and voltage. Ampacity is current and voltage is potential. Well, potential is a little bit ambiguous. A good analogy for voltage is pressure. Well, pressure to me is a little ambiguous too. I like to think about voltage in terms of potential. I really don't know what potential is, but I know what potential energy is. Think back to my mechanical engineering classes. I think about, a weight suspended on a pulley way up in the air versus a weight down on the ground. The weight on the pulley has a lot of potential energy. The weight on the ground doesn't have any potential energy. And it's just an analogy, but that's the difference between, say, high voltage and ground, or high voltage and low voltage, is how far up that weight on that pulley is going. Whereas current would be more akin to if you were converting that potential energy into kinetic energy, it would be how much rope is being pulled around the cross-sectional area of that pulley, how much mass of that rope is flowing through that pulley system as the voltage is transitioning from its high potential to its low potential. Ampacity is more like flow rate, whereas voltage is more like potential energy. And so electricity is going to flow from its high voltage to its low voltage, and its flow rate is going to be current. How many electrons are passing through that cross-sectional area is current, and the transition between high voltage to low voltage has a little bit to do with that flow rate as well. A volt times an amp is a watt. A volt times an amp has no time component to it. A watt hour has the time component to it. So voltage and amperage are still units that are kind of frozen in time. And what's a little odd to me is our voltages are really nicknames. And when I talk about a 120, 240 volt system, and I go out to my electrical grid and I stick my voltmeter up to my service panel, in a rural area, they're going to be running the grid at a higher voltage than 240 volts. You might have a grid be 250, maybe even 253 volts. It's higher than 253 is higher than 240. That rural power plant, to push power all the way to that really remote cabin at the end of the line has to uptick their voltage a little bit more compared to a more concentrated city. But we'll still call the grid 240 volts, even though it's being operated at 253. Same thing with batteries. This is really confusing, but if I'm installing a 48 volt flooded lead acid battery, and I go and I put my voltmeter up to it and it reads 48 volts, I'm actually almost drained my battery. Now I drop down below 48 volts and my system's not going to work. I've charged that battery all the way up. It may get up to 55, 56. A sealed battery cannot take as much voltage as an unsealed battery. I blow that sealed battery all the way, that balloon, I blow that balloon all the way up and I knot it and I go throw it on the grass, it might pop. I take that same balloon and I blow it all the way up and then I let the air out. It's going to last a while. I can do it again and again and again. And so an unsealed battery might be charged, that's a 48 volt battery bank, might be charged up to 57 volts. And when I'm overcharging the battery to condition it, I might get it up to 59 volts. Whereas a sealed battery may only charge to 56 volts, and overcharging it for conditioning it is generally not allowed because you might pop it. And so voltages and nominal voltage is just nicknames to say, okay, this is a 48 volt battery bank's the convention. You need a 48 volt charge controller, but there's a range of operating voltages beyond that. In AC design, we call our circuits branch circuits, or if they're supplying power, we call them feeder circuits. In solar speak, we call our solar circuits strings. Well, that's not really that's more jargon. It's not really a National Electric Code term. National Electric Code really doesn't have a jargon for solar circuits. They just call them DC feeder circuits. Well, the next definition is a continuous load. And that's a load where the maximum current is expected to continue for, say, 3 hours. And so let's that's as opposed to a non-continuous load that would be less than 3 hours. And so when you're sizing the circuit ratings of these branch circuits, I don't know if any of y'all have ever tripped the main breaker of your house. But if you go and look at your service panel, you might have 200 amp electric service, but if you count up all the breakers on your service panel, you might have more than 200 amps worth of breakers. You might have 300 amps of breakers. Well, the way those breakers trip is the current flowing through the conductors heat up, and that heat will pull on the breaker and open it up, turn it off. And so actually your breakers and your circuits can handle a little bit of a surge without tripping, where a 20 amp breaker, you might be able to push a little bit more than 20 amps through that breaker for a very brief period of time, and then it'll switch. And so you go and you turn on every single appliance in your house and start pulling 300 amps of power through that service panel, you may very well be able to pull all of that power through your panel for a brief period of time before that main breaker gets hot enough to trip. And we see that reflected into our circuit sizing, where our AC branch circuits are sized to have an ampacity of whatever the non-continuous load is, whatever the short-term loads are, whatever the 3-hour or less loads are. But for any load that is going to be on for more than 3 hours, you have to apply an additional safety factor of 25%. And so on our solar circuits, our solar array is going to be on for more than 3 hours a day, and we have an ampacity adjustment of additional 25% because of that. So if our solar array requires 40 amps of power, and we know for 3 hours a day or more it's going to be outputting 40 amps of power, we don't want our breaker to trip. And so we give it an additional 25% capacity so our breaker doesn't trip. So which of these loads are continuous and which of these loads are non-continuous? Well, we already talked about the solar array, but what about our air conditioner? We're not running our air conditioner 24 hours a day. We may only turn on our air conditioner when we get home. But it's going to be on for more than 3 hours. That's a continuous load. Our solar array is treated, even though it's a line, even though it's supplying power, we treat it as a continuous source. Your refrigerator. You may read your manual and you'll realize that refrigerator compressor is turning off and turning on and turning off and turning on and turning off and turning on. Even so, even though the appliance is going through a duty cycle of turning off and turning on, it's still plugged into the wall 24/7, operating 24/7. Your refrigerator is a continuous load. Your washing machine is not a continuous load. That washing machine is going to be on for, maybe a half an hour or 45 minutes and then turn off. So the washing machine out of these appliances is the non-continuous load. If I'm doing a load calculation, I would do my air conditioner unit plus 25% and my refrigerator plus 25%, and then my washing machine and not do the additional 25%. There's continuous loads and there's non-continuous loads, and by and large, the rule is your non-continuous loads you size to be the ampacity of the cable and the ampacity of the breaker, but your continuous loads get upsized by 25% with regard to their amperage. Now, voltage has other rules regarding its size. So, hey. So with voltage, we're not really talking about how many electrons are flowing through the cross-sectional area of our cable. What we're trying to make sure is that we're powering enough for whatever that pulley with the sack of weight up in the air, when it's in use and it's transferring that weight all the way down to its low voltage, that it's powering whatever load we're trying to get it across, but that pulley has friction on it. And not talking in analogies, but talking in reality, that friction is voltage drop. the heat, the friction that the electrons are going through as they pass through that copper is going to take a little bit of power out of the system. And so if we're at 240 volts at our service panel, you may have opened up your refrigerator manual and it's like, oh, this is a 210 volt or 220 volt device. And you're like, well, I thought I was on a 240 volt system. So why is my fridge 220 and my service panel 240? And it's like, oh, well, they're making sure by the time you get to that plug and you plug into the wall that you're under load, that refrigerator is going to turn on and cycle. And there's rules regarding how much voltage drop is acceptable to your load so that you can still deliver power to operate your devices to those outlets. The general rule of thumb is to design around a 3% voltage drop or less. And often it's going to be cost effective in solar to design around a 2% or even a 1% voltage drop. Spend a little bit more money upsizing your copper, get more power out of your system. The relative cost difference to upsize your copper from a 3% voltage drop to a 1.5% voltage drop is going to be less than adding 1.5% to the cost of your project. So generally you're going to aim for less voltage drop than what is the minimum requirement by National Electric Code. What does a 5% voltage drop actually mean? So let's say you're like me and you want to build your little off-grid cabin in the woods. And you might say, well, what if I keep everything on DC? And so I might choose between a 12-volt battery bank or a 24-volt battery bank or a 48-volt battery bank. A 12-volt battery bank is like your car battery. That's 12 volts. 24 volts is like a motorhome, an RV. You might be living in an RV, and it might have a 24-volt battery bank in it. And a lot of off-grid homes are built at a 48-volt battery bank. So let's say you went just DC only. You wanted to have a DC house because you're eccentric. Well, a 5% voltage drop using number 8 cable is pretty common in solar to use number 8. Sometimes they use number 10. But you'll get a 5% voltage drop with number 8 cable on a 12-volt circuit at 20 feet. And so anything that's further than 20 feet away from your 12-volt battery, if you're using number 8 cable, it's probably not going to power up. Well, a recreational vehicle, an RV, might be longer than 20 feet. It might be 30 feet. It might be 40 feet. And so, that's where you get into higher voltage batteries on RVs, going into 24 volts so that those DC appliances will still run at the back of the motorhome. But still, you're talking about, a one-room cabin and not an actual house. And furthermore, most homes are more than 80 feet long. And so that's where you might want a higher voltage system. So in fact, we don't do DC circuits in the US, not really because DC is worse than AC, but more that we have to step the voltage up to transfer it over long distances. And historically, and still so today, it is cheaper to step up that voltage by converting it to AC because of the equipment, the transformers required to step up that voltage are cheaper to do with AC rather than DC. And so even though there's a lot of technical reasons why DC might be the better form of electricity, the reason why AC won out for transporting electricity is that it's much cheaper to step up the voltage using AC transformers rather than DC power converters. And that's only now beginning to change because, due to not the industrial revolution, which was, turbines and engines and AC based, but the computer revolution, which is more DC based, putting more investment into DC power converters and electronics to compete with AC transformers. All right, feeder circuits. All circuit conductors between the service equipment and the source of a separately derived system or power supply. So these are your power circuits. A solar circuit is a feeder circuit. Your power circuit is a feeder circuit. These are supply circuits, are feeder circuits. So feeders that are not more than 600 volts are sized in the same way as branch circuits. When we're sizing our breaker on our circuit, you're rounding up to the next breaker. And so you say, okay, well, I have a 40 amp solar array and I need to do 25% larger than that. And that's that's 50 amp breaker. So you put it on a 50 amp breaker. If I had a 42 amp solar array, I upsize it by 25% and I get somewhere around 51 amps. And so I upsize it to a 60 amp breaker. And you say, well, is that going to trip? Well, yeah, it will. It will allow more than 25% additional load through, but at the same time we have conventional breaker sizes, and downsizing it might mean that it's not going to operate correctly by pushing out 40 amps plus the additional heat that pushing out 40 amps is going to generate. If you undersize your breaker, it may trip. If you go and you put in, if you go in and you have a 40 amp device, like a 40 amp inverter, and you put it on a 40 amp breaker, once it hits its maximum output capacity for an hour or so, it's going to need more current than that. It's going to trip your breaker. Grounding is the 0 point. And so we don't want any of our metal parts to have electricity in them. And so we need to connect all the metal parts on our electrical system together and connect them to ground. The very last connection to ground is called the grounding electrode conductor. Everything before that very last connection to ground is part of your equipment grounding system. And so looking back to this wire diagram, here we have our equipment ground conductor. And that's not always copper landing on each individual module. What's common in the solar industry is to have the clipping system that connects the panels together, to have that clip be listed as a ground path so that you don't have to do any of this stuff. You can just have one connection to ground at the edge of your array with clips. So here's your equipment ground conductor coming back to your service panel. And that's going to land on a ground bar that has all, other circuits and stuff landing on the ground, landing onto it. And then this very last connection point to ground is called your grounding electrode conductor. And that connects to your grounding electrode. So the ground part is not that complicated. What gets a little bit more complicated is this other wire called the neutral. And the reason is the neutral can actually be a current carrying conductor. It's just not designed to carry current. It carries, imbalances between phases. It's kind of the home run for your electricity to go into your device, and then it needs to come out of the device and back to its 0 point potential. And so there's one point on your electrical system where this neutral is connected to ground. And that'll keep this neutral at a 0 point so your electricity can flow from its high potential, back through the neutral and then get carried to ground. And so, don't get confused. The neutral conductor is absolutely a current carrying conductor, even though in most circumstances it's not carrying current. But it still can shock you, if you touch it. You might take your voltmeter and monitor your neutral, and it might say 0 volts, but then, so a circuit turns on another part of your building, and that voltage will uptick. And so we have the grounding electrode, which is like your ground rod or ground plate that is establishing the physical connection between the earth and your home. You have the grounding electrode conductor, which is the actual wire that connects your home to the grounding electrode. And the reason why it's given a separate name is because it's a larger wire. You think about the plumbing that goes into your house. You might have a 4-inch pipe connected to your sewer system, but the plumbing in an individual toilet might only be 1.5 inches. Similarly, the ground path between all your devices may be using smaller ground wire, but the very final stop is the drain to the whole house. And so that final stop, that grounding electrode conductor, is going to be a larger size than the other ground wires on your system that bring it all back to that point. The grounding electrode conductor is the Mississippi River. The equipment ground conductors are all the tributaries that feed into it. And so now we can identify our equipment ground conductor, our service point, our service entrance conductors, which are feeder conductors, but they're designated to be more than feeder conductors because you could have a feeder conductor feeding another subpanel. And so this is a feeder conductor that's feeding a subpanel, but it's not a service entrance conductor like what's coming in from the grid. Now, I would call your solar conductors service entrance conductors as well, but there's a clear point of distinguishment between this circuit that's landing on the distribution side or the load side of your service panel, as opposed to if this same solar circuit were instead landed, still on the customer side of the meter, but on the service entrance conductor. So technically, Your solar circuits are going to be service entrance conductors if they're tapped into this side of the breaker, whereas if they're tapped into the distribution side of the breaker, they're only going to be feeder conductors. And I don't think the terminology, whether you call it a feeder conductor or a service entrance conductor, is the important part. I think what's important is to understand that there might be a design difference between coming into the supply side of the service panel versus the load side of the service panel. And so we're going to talk about those nuances as we continue on with class. But basically, code will start out with, since we're on this slide, it's a good time to point out that you are going to be at your main service panel, which is the main panel for the building. And it depends where. Sometimes this is done inside the meter box. Sometimes it's done outside the meter box at the service panel. Sometimes there's a disconnect switch where this is done. But at one point, you bond the neutral to the ground. And this is where the point we were making right before the break comes into play, because you might have a service panel here coming in where multiple solar circuits are landing on the service panel. Like if you have more than one solar array, more than one circuit of solar, in this case these are microinverters, but you might have multiple solar panels with multiple inverters coming into a distribution panel versus your main service panel. And so a very common design error is when you bond neutral to ground. You only bond neutral to ground in your service panel, not in your distribution panel. And so if you have a distribution panel here that might look exactly like your service panel, but it's coming in on the load side of your panel, you would not bond neutral to ground at this point. Because if you bonded neutral, you might have a ground connection at this point. If it's on a separate building, but you're feeding one neutral all the way through. But if you take your neutral line on a distribution panel and you connect it to ground, now you have multiple places where the neutral line is connected to ground. And so almost like a leaky boat, if you bond your neutral to ground in a distribution panel, electrons could leak out of your system before being carried all the way back to your main service panel. And what that would do is cause your ground fault system to fail. And so you could have a ground fault that doesn't trip a breaker, and that could cause a fire, burn your building down. And so, we'll get to it, probably pretty soon. But if you have a service panel rather than, on the utility side of the breaker. So we're doing this right now on our commercial solar array. We're not connecting it to the load side, we're connecting it to the supply side. And there's some nuances to that that you get into in the solar specialty section way down at the end of this program. The gist of it is when you connect to the service side, you can do up to 100% of that main breaker rating. If you connect to the distribution side, you can only do 20% of this service panel rating. And so you can do much larger arrays when you go into the service side, the supply side of your electric service rather than the load side of your electric service. Now, many customers do not need large systems to offset 100% of their bill, because even if they're only using that 20% capacity, they're not using their entire breakers on their panels 24/7. So they're not, those breakers might be off 90% of the day and only on 10% of the day. And so it's very possible to connect a solar array to the load side and offset 100% of the bill. But if your home is large, if your home is not energy efficient, you got to go into the supply side. And so going into the supply side, you may have multiple connections where you're bonding your neutral to ground. And so you may just bond your neutral to ground and carry your neutral wire on back. Now, we're going to get to that in a little bit. We have another question that says, calling a refrigerator a continuous load is a little misleading because the refrigerators are seldom operating continuously if someone leaves the door open. That refrigerator is plugged in 24/7. I would not say that a refrigerator is on for less than 3 hours a day, as opposed to, say, a washing machine, a dishwasher. So circuits derived from auto transformers. This is starts to kind of get complicated. Feeder circuits shall not be derived from auto transformers unless the system supplied has a grounded conductor that is electrically connected to the auto transformer grounded conductor. What does that mean? Well, I wanted to mention this to introduce the concept of a grounded conductor. We said the neutral conductor kind of acts as a home run for your electricity, a return path for your electricity to the panel. It acts as the 0 point that pulls the electricity from its high potential down to its low potential. And we create it to be that 0 point. That doesn't mean that it doesn't have current flowing through it, but we create that 0 point of reference by connecting the neutral to ground. So your neutral conductor is your grounded conductor, as opposed to your, what are called hot conductors, your 120 volt legs are your hot conductors, and they're not connected to ground. And so basically what this auto transformer rule is saying is that feeders should not be derived from auto transformers unless the system has a neutral that is electrically connected to the auto transformer's neutral. Okay, well, without getting into the technical definition of an auto transformer, the neutral of your service panel is connected to the neutral being supplied by your utility meter. Your neutral from your solar battery inverter is connected to the neutral in your home. And so here's, say, a SMA battery inverter, and the SMA battery inverter outputs 120 volts. Well, residential homes in the United States are not 120 volts. They're we call it 120 240 split phase. And so if you want to power a 240 volt circuit in parallel with 120 volt circuits like we do in a standard US home, you need a 120 240 split phase power supply. You want to do that with a 120 volt output inverter. You need to put a transformer between the two that'll take that battery output that's 120 volts and step it up and give you 120 240 output. And so here's a line diagram where we have a battery inverter, a 240 volt solar inverter, now this looks like a 120 volt generator and a 240 volt, 120 240 volt input from the grid. And so here's a transfer switch, and what you can see is the neutral wires here are all bonded together. Now, do you have to bond the neutrals all together? The answer is not always. But if you're deriving your power from this kind of system, then the neutral of the load needs to be connected to the neutral of whatever's powering it, whether it be the generator or the battery inverter or the grid. Now, it is possible to add another disconnect here and disconnect your neutral, but you're only allowed to disconnect that neutral if simultaneously you're disconnecting the entire power supply from the rest of that grid. So why would you want to disconnect the neutral entirely? Well, you might be facing a grid interconnection rule that says if you're connected your on-site power system to our grid, we're going to add additional solar discriminatory fees to your electric service. And so you'd say, well, I'm going to have a transfer switch that completely disconnects me from the grid when I'm being powered by my solar battery. And then, maybe depending on, how your switchgear is designed, if your solar battery is fully drained, like let's say there's a hurricane and there's just clouds in the sky and your batteries are drained, you could reconnect to the grid and run off grid power by switching between the solar array and the grid power. The utility who wants to charge you for your solar connection may still not like that and say, well, if any of your wiring touches any of our wiring, we're going to consider you to be grid connected. Why you wouldn't want to disconnect your neutral but keep it connected is so that you could have a more elegant system that senses when the grid turns off and switches you over to battery power, and then senses when the grid turns back on and switches you back over to the grid power, rather than creating a completely blind disconnection, kind of using the neutral as a signal. And so the point is, if you're being fed by a generator, if you're being fed by a solar array, that neutral needs to be derived from your supply. When we talked about nominal voltages, nickname voltages, this is a picture of a 120/240 residential electric service. What we have is our higher voltage power lines coming into that transformer. It's being hung on the side of the pole here. And then based on copper windings and induction, they're deriving what's called a 120/240 volt split phase residential system, where you have a neutral reference point at 0 voltage and a 120 volt leg and a 120 volt leg. And so you can pull off 2 legs of power to get 240 volts with respect to your grounded conductor, with respect to your neutral. To say with respect to ground is correct and incorrect. To say it's with respect to ground, well, the neutral's grounded. The neutral's connected to ground, so you have a 0 voltage there, and you're pulling out 120 or 240 volts. But it's not like this 120 volt circuit is directly connected to ground. It has to return through the neutral. If on the load side we had a separate neutral to ground connection, then that return circuit might not make it all the way back to your service panel, and so that the grounded connections in your service panel may not function. And so we can pull 240 volts off this. We can pull 120 volts off of this. This is kind of the symbol for it. Looking at some service entrance components, we have this weatherhead. This is a drip loop. You look at this tangle of wires coming down and you say, well, that might look a little bit ugly. Well, what it's designed is so that when these wires get rained on, it drips out of the box rather than going into your service equipment. And we think about that on the rooftop, on how our outside of conduit solar cables enter the transition box that goes into the attic. Do we want to run those cables in from the top on a slanted roof or into the bottom on a slanted roof? Running in them from the bottom is going to be arranged to drain, so that when the cables get water on it, the water shoots off the cable but doesn't make it into the box. Here's that transformer that takes the high voltage line and then converts it, steps it down into your low voltage service. In this case, 120/240 volt. When they go and power down a building to perform solar supply side interconnections, the utility takes a pole and they lift up these breakers to disconnect them. They have really tall fiberglass poles that they just poke at the top of the wires to lift them up. So the neutral conductor is a conductor that is intended to carry, it's intended to carry current under normal operating conditions. It allows you to have that device to have a 0 voltage point of reference so that electricity can flow from high voltage to low voltage without that electricity escaping to ground until it gets back to the main service panel. And there's different kinds of electric services, with different wire diagrams. So here's one that's just a 240 volt leg with a neutral and ground. It looks just like this 120 volt, except that the power derived from it will just be 120 volts, whereas split phase is two 120 volt circuits that could be combined to produce 240 volts. You get into commercial systems, instead of just having one or two legs, you have three legs. And so here you still can have 120 volt appliances. And then if you combine two legs, you get 208 volts. So you might actually get into different kinds of commercial motors and commercial equipment, depending on if you're on a 120 208 or even a larger 480 volt commercial system. Depending on how the transformer is wound, this is called a Y winding because it kind of makes a Y. This is called a delta winding because it makes a triangle. And these are different electrical systems that will power different motors, different components. When you're designing a solar array for a three-phase commercial system, you need to know if you're on 120 208 Y or 277 480 delta, because not all the inverters can be wired for delta versus Y configurations. Normally you'll have to change some fuses around on the inverter if it might come pre-wired for a Y configuration. You might have to change it around a little bit per the inverter manufacturer's instructions to switch it over to a delta configuration. And so you still might have in a commercial building 120 volt circuits that you can plug into the wall, but they're industrial air conditioners are going to be custom purchased for whatever electric service is into that building. Now, here's an interesting code rule. When you're doing your amperage calculations, those calculations shall be permitted to be rounded down to the nearest whole amp. And it says with decimal fractions smaller than 0.5 drop. That last little tidbit's kind of unnecessary if you're rounding down your calculation to the nearest whole amp. And so as engineers, we may be into like significant figures, trying to maintain the integrity of our decimal point all the way through our calculations. We have to remember that when you're using the charts found in National Electric Code as opposed to an engineered calculation, these are fudge factors. And they say, well, you can just use whole numbers rounding down. So when you're required to list your operating amperage of your system on placards, you don't need to put in decimal points. You can just keep nice whole numbers. So when you're designing a home, a new construction, how do you know how large of an electric service panel you need? Well, National Electric Code governs that, and in our branch circuit calculations at the beginning of code, they give you rules of thumb to say, well, if you don't know what your load is, such as in new construction, follow these particular guidelines. For motors, lighting, stoves, ovens, pretty much any electrical device in your home. So it says the minimum load of a service or a feeder supplying a panel is going to be the sum of all these loads calculated after any, discount factors are applied. So what does that mean? Well, we're going to get to this one later. As we said, not all your devices are going to be on at the same time. And particularly when you get into, say, design of a hotel, not everyone's running their air conditioner at the same time. Not all the refrigerators are going to be clicking on and off at the same time. And so the more appliances you have, the greater a discount factor you get to apply to the load. You don't have to count all of the dryers in a laundromat as being on at the exact same time. Some of this, we're going to start using this term AHJ. It stands for the authority having jurisdiction. That's your local electrical inspector generally, although your power company may be different than the electrical inspector. The inspector may be a civic function or municipal function, whereas a power company, may or may not be giving you an inspection, but they still may or may not have guidelines. Usually they will have guidelines for interconnecting your system to theirs. If you don't know the rules and regulations for interconnecting systems in your local area, there's a website called desireusa.org. I'm going to put it in the chat box. This is a work-friendly link. It's just desireusa.org. You click on it and get a map of the United States. Click on your state. Let's just go with, I don't know. I'm in West Virginia right now. I use this little search tool. The Desire website will give you a lot of different information. So information on net metering, any state programs that are available. I'd say, in energy efficiency programs. It's not just a solar or battery websites. You get information on federal too. And so here we have the West Virginia interconnection standards. And so tell me some various interconnection standards and different fast track processes for large or small systems. So there seems to be a level 1 for systems that are 25 kilowatts or less, level 2 for 2 megawatts or less. References some state codes. And then it gives me contact information for the Public Service Commission, which may be a good starting point if you're trying to find out more about interconnection documents. And that's going to vary state by state. As we see in this slide, it's referencing the actual different power companies in the state for their individual interconnection guidelines. The feeder or service loads, the maximum unbalanced load is the maximum net load between the neutral conductor and any one ungrounded conductor. And so you take the load that's expected on one phase and the load that's expected on another phase. So let's say you have, some heavy duty air conditioning equipment that is 240 volts, 120 volts per leg, and you got 3 legs. So you tie your air conditioning unit into 2 of those legs, and let's say that's a 15 kilowatt air conditioner, and your other leg doesn't have anything. And so you could have a load imbalance of 15 kilowatts, between the neutral conductor and one ungrounded conductor. So, when you're filling up your service panel, you're trying to divide your loads as evenly as possible and reduce your maximum unbalanced load between the neutral and any one ungrounded conductor. And fundamentally, what that means is that your neutral is not carrying the current, the entire current of one leg back to ground, but it'll be carrying the unbalanced load back to ground. And so that'll allow you to have an undersized neutral. But for renewable energy systems, you are typically using a full-sized neutral. So I do not recommend undersizing your neutral for renewables like you would with other kinds of loads where you might get an undersized neutral in your Romex, something like that. So looking at homes, you say, okay, well, there's a 10 kilowatt general load. Well, one question is, well, how much load is a typical 200 amp service panel? When you take a 200 amp service panel and you multiply it by 240 volts, and so what that says is your typical 200 amp service panel, the maximum continuous load that it can supply, a volt times an amp is a watt. And so your typical residential service panel is capable of delivering 48 kilowatts of power before it trips that main breaker. So how do we get to that point to say, well, a home needs 48 kilowatts of power, a home needs 200 amp service, or maybe 48 kilowatts is not enough and your home needs 400 amp service? And they say, okay, well, adjust 3 watts per square foot for the house times 40% for lighting, 10 kilowatts right off the top. Every 20 amp branch circuit is another 1.5 kilowatts. So that's not every power outlet in your home, but that's how many, a branch circuit will have multiple power outlets. So every 20 amp branch circuit is 1.5 kilowatts. And the 100% of the load for your appliances, cooking equipment, dryers, water heaters. So in this case, for doing our general load calculation, we're not upsizing by 25%. Remember that upsize of 25% is for our conductors, so that when our conductors are carrying 100% of that continuous load, that they're not overheating. There's different use cases for determining your load for your heating and air conditioning, and usually it's something along the lines of looking at your maximum air conditioning load in the summer, your maximum air conditioning heating load in the winter, and understanding that they're not going to be both used at the same time, and so using the largest of the two, so you don't have to add your heating load to your air conditioner load. Apartment buildings can scale all the way down to 23% discount. We have a question. Well, 20 amps times 120 volts should be 2,400 volt amps or 2.4 kilowatts. And so, yeah, that would be the maximum that a branch circuit can carry continuously is 2.4 kilowatts. And so they're giving you a discount factor because they're assuming that not every single branch circuit is going to be overloaded. So this is for determining what size of service panel you need in your home. So they're assuming you're not going to be going and blowing out every single circuit in your entire house and tripping your main breaker. And so then there's different discount factors for apartment buildings, schools, farms, different kinds of buildings. All right, so I pull open my electrical account online and I can look at my load for my home. I can say, well, my continuous load is not getting anywhere near 48 kilowatts. In fact, my maximum load for the year is around 14 kilowatts. And so if I went and said, well, do I need 200 amp service? Could I use a smaller electric service instead, like 125 amps? The power company might come back and say, no, we want you at the larger service, but you can actually use your real-time data to determine the maximum size of your service panel if you have, what this says is 1 year of operating data, or if you're in like the South, you had 30 days of load conditions. So this might be like, let's say you're building a new construction home and you build the house and you're running off temporary generators, and you're right on the line of needing a 400 amp service or a 200 amp service using all the fudge factors. And you only want to do 200 amp service. Let's assume in this case, this is not always the case, but let's assume the utility is going to charge you more for a 400 amp service versus a 200 amp service. You're allowed to base your application off of existing loads. Then again, how often is that really going to be the case? We're getting into some more definitions. What is the definition of a building? It's a standalone building that is cut off by firewalls. A garage is a building. Bonding is it's similar to grounding, except it's not assuming you're establishing your ground path just by bonding stuff together. Bonding is establishing that electrical continuity that then gets hooked up to your ground. So it's almost grounding, but not quite. And so here's an example of a bonding jumper that is electrically connecting one stick of rail to another stick of rail, because this splice in between the two sticks of rail is not listed as a ground path. And so if I'm only running a ground up to the corner of my array, then my racking system and my modules have to be all electrically connected through the module clips, except the module clips are going module to module, and maybe depending on your array, you got the modules ending here and starting over there, this is grounding our rail to rail together. Sometimes the module ground path will do that for you. It'll jump over that rail gap, but you don't absolutely know that for sure unless you're doing, CAD modeling and knowing where all your clips are going to land. And so the question is, what you need to think about is how is all the metal parts being connected together. Let's do an example where you're bonding the metal rail, the metal frames of the solar panels to each other through clips. And let's assume the clips are listed to carry the ground path from the module clip down to the rail where the modules are landing on. You may not necessarily be bonding the rail and the attachment feet to this metal roof. And so, your metal roof may or may not be grounded. You can't just say because my metal racking structure is connected to this metal roof that is a bonded system. Which usually means you need to carry your equipment ground conductor all the way up to the roof and land it on your rail so that your rooftop solar array is grounded. You can't just say because my solar array is attached to my building and my building is grounded that my solar array is grounded to my building. To make such a claim, you would need to actually bond the racking system to the metal roof itself. And so that gets us back to kind of what we were talking about right before the break is where is the main bonding jumper that doesn't just connect rail to rail or module to module, but actually connects all our metal parts to ground. We're going to keep exploring that. When we get into a definition of a substation, this one really isn't that important to the class. I kind of stuck it in here as a historical note. So the definition of a substation is an enclosed assembly of breakers, switches, and circuits under the control of qualified persons through which energy is passed for the purpose of switching or modifying its characteristics. There's a rule that says wherever the substation has a connection to high voltage, such as your very high voltage power lines, that you need a line diagram showing that connection. And so it's a very common requirement for your solar inverters to have a line diagram posted onto them, and that is usually an AHJ rule for commercial systems. They like to see a line diagram posted. And as far as I can tell, that rule comes through rules governing substations. So this definition is on the quiz. Just a substation is an enclosed assemblage of equipment under control of qualified persons. It's fenced in. You're not able to go into a substation. Only qualified persons are allowed in, which are used for, stepping the voltage, up from the power plant into your high voltage power lines or back down into your, medium voltage power lines, your distribution circuits that will then be further stepped down by those transformers hanging off the side of the building. So outside branch circuits and feeders, are they allowed? Are you allowed to run power lines down the side of your building? So the answer is yes. And there's rules that govern what kinds of conduit these outside of the building power lines can be run through. And so let's talk about how we run power lines, outside the building, such as up on the rooftop. We have a definition of a raceway, which is an exposed channel of metal or non-metal designed for holding wires, cables, or bus bars with additional functions as permitted by code. So right now I'm building a commercial solar array, and it covers the whole roof. And so there's wires coming out of the back of these panels that are covering the whole roof. And the question is, well, where do you put them? How do you get all of your wires from underneath the array back to where the equipment is, back to where the inverter is? And so, while solar cable is rated to be outside of a raceway, be outside of a conduit, such as on the underside of the panels, and we have little clips that we use to clip the cables up to keep them up off the roof. As soon as you hit the perimeter of the array, you still have to get your cables back to, the equipment that might be on the side of the building or the inside of the building. So this is actually where we see, on the system I'm installing, it's kind of interesting because the racking manufacturer gives us some cable management clips that are metal, and then they put a little note in the cable management clips that says, if you're using a metal raceway, National Electric Code requires that metal raceway to be grounded, and our cable management clips are not grounded. Well, they're kind of just telling you that their cable management clips violate National Electric Code. I have in my current design, I'm a subcontractor on this one. Let me bring it up here. And what we can see here is the array layout. And so all throughout this area, we have cable. All throughout this area, we have cable. Now, on a small array section like this, we're just going to bring let me change my pin color. We're just going to bring our solar circuits kind of clipped to the undersides of the modules back throughout the array. This section right here only has about 4 solar circuits, and so we're clipping our cables up and bringing our 4 home runs out to the back to the edge of the array, and our inverter is being mounted right here. But the question is, well, now how do we get from point A to point B? Or on this larger section here, every 2 rows is a circuit. And so our circuit starts here and then loops up and it comes back down. And then we're on our next circuit, and then our next circuit, and then our next circuit. And so we don't just have 4 circuits in this section, we have tons. And so if we kept all that cable clipped up on the underside of the panels, just the sheer amount of circuitry, even though it's rated to be outside of conduit, bundling it up and clipping it up underneath the array creates a mess, a big tangle of wires. And then you might need to jump your circuits. You might need to move from this section to the next section, or this section to the next section, and move your array across where people are walking. And so you may need a little stairwell to make a little bridge to go over your cables. And it begs the question, well, what are the cables going in? And so in this project, the client specified that the cables should be tucked into EMT conduit. EMT conduit would be a metal raceway. And so on this particular design, and we'll look at this big section because it's kind of the most interesting. What we have is every 4 or every 2 circuits, we have a stick of EMT conduit coming and then running back to where our inverter is landing. So every 4, we have a stick of conduit coming. Every 4, we have a stick of conduit coming. And EMT conduit is not the only way to do this. But basically now we have lines of EMT conduit being held up by pipe blocks, kind of racing down the edge of the array. And you could use what's called a cable tray instead of EMT conduit instead. There's different kinds of raceways. Remember, raceways are channels of metal or non-metal expressly designed for holding wires, cables, and bus bars with additional functions as permitted by code. So the big question that I have is it better to have these raceways to be metal or non-metal? Well, if they're metal, they have to be grounded. And usually that's not a problem. Usually you're going to land these conduits on a box and then land your inverter on the box, and the connection between your conduit and that box is going to ground that end. But let me show you how it's typically you're going to transition from this array into this raceway. Now here is a fitting. It's called a cable gland, or they're calling it a masthead. And your solar circuits just kind of fit inside that. And that makes a nice seal so water can't get in, so critters can't get in. And your conduit kind of fits onto it. And so now you're in your EMT conduit coming out the back of it. But the problem is, to ground this metal conduit here, you really need a grounding bushing to connect on to, say, your solar rail, which is presumably grounded elsewhere. And this cable gland is not compatible with a grounding bushing. And so really, your metal raceway, it needs to be grounded. To ground conduit, you need to ground it on both ends of your conduit run. And so what I would say is that plastic on a rooftop is a better raceway for your solar cables, particularly if you're using these plastic cable glands. Now, if that was all French to you, I'm going to show you a picture of a better cable gland with a grounding bushing on it. And so here's a cable gland made by Arlington. And what you can see is they say, okay, well, this is for having your metal conduit run out. And we know we need to ground both ends of our conduit. And so we assume you're landing on the box on one end, and that end is going to be grounded to the box, and the box is going to be grounded to whatever's going out the other side of the box, and that's going to be grounded to another box, and that's going to be grounded to your system ground. So you've established an effective grounding path all the way down. And what they've stuck on here is an actual grounding bushing where you can take your equipment ground and land it on this grounding bushing and then keep going and land it on your solar rail. And so now your solar rail's grounded and your bushing's grounded to your solar rail, and then you're grounded at the other end. And then this is your effective ground path or your equipment grounding conductor going all the way back. So this is really a much better, if you're using metal conduit and you're just kind of ending your metal conduit, you're not landing on a box and you just want to dump your cable out of it. And that would be very useful because by being able to dump your cable directly out of the conduit, you don't have to buy a box. You don't have to put a ground bar in the box. You don't have to transition out of the box. There's, and the problem with boxes is they don't fit well on a roof. This conduit you can sneak underneath the panel so that you don't see ugly conduit running across the rooftop. You can just keep everything underneath the array nice and neat. A big 6x6x6 junction box or larger, you're not going to have enough space underneath most solar arrays to fit a large metal box. There are some solar specialty boxes that will fit underneath. The only problem with this fitting is that it's only designed for 2 solar cables. And so if you have dozens of circuits on your rooftop, you need dozens of conduit runs and dozens of cables, whereas the Hakko plastic connector can have multiple holes, handle multiple conductors. And so really, then in this design, the client is specifying EMT conduit with 4 conductors inside each conduit, but there's no good way without, installing a box here and then grounding the box to the panel, just using a simple cable gland. There's really no good way to come out with it. And then furthermore, we go and look at this particular inverter system that we're using. So like here is where they're specifying, 4 solar cables inside of one plus a ground inside of one conduit. And that's kind of the argument that in inspection we're going to make is, hey, we got, giant long links of bare copper wire, inside of that conduit. It's not a great argument. But then normally that conduit is going to come back and land on a trough, and your inverter is going to run into a trough. But this is a brand new solar inverter that is designed just to sit down on the rooftop itself, and the outside of conduit solar cables plug right into the side of this inverter. Well, the solar cables are rated for outside of conduit, and you could just run them all through the array in an exposed raceway. And if that exposed little brackets are metal, so let me pull up another picture. So here's like a little metal cable bracket that would form a raceway for your solar cables to be all bundled up in, and these kind of clip into the module frame, but not through a ground path. And so these are metal. If they were plastic, they wouldn't be a code violation. But because they're metal and they're not grounded, and code says your metal raceways have to be grounded, it is a code violation. Or instead of running it through these clips underneath the array, you can pull the cables out of the array, put them into EMT conduit, and we can kind of see where the industry is starting to make cable management systems that avoid running everything into boxes before going into conduit, so that you can just go straight into conduit, but that the grounding is still catching up. Then again, if you're just running into PVC rather than metal conduit, something like this plastic connection is just fine. But now we get our metal EMT conduit to right here and transition out of one of these plastic cable glands, because instead of landing on our box, this unit is designed just to be sat down on the roof and have the solar array plugged directly into it. And so it becomes problematic, because now neither end of the EMT conduit run is connected to ground. It really should be a plastic conduit run, but they're insisting on EMT. So, when you're looking at your inverter selections and you're thinking about how is that cable going to transition between the array and the inverter, all of your metal raceways that hold your cables need to be grounded. And, the mindset of the client might be, oh, metal conduit is going to be so much better than plastic conduit. But that metal conduit needs to be grounded, and there's not really good ways to go directly into conduit without landing on a box first. So then we have enclosed raceways. So not all raceways are enclosed. Enclosed would be surrounded by a case, housing, fence, or wall that prevents persons from accidentally contacting energized parts. So there may be a requirement for an enclosed raceway. What's a ground fault? A ground fault is an unintentional electrical path to ground. Let's say you have EMT conduit racing across a rooftop. You can only have a 120-foot section of that EMT conduit before thermal expansion will start to cause that EMT conduit to pull itself out of its fittings, to pull itself out of that box. And as far as I know, the solar fires that have burnt down commercial buildings in years past, the one problem was that they used to take the negative side of the solar inverter and connect it directly to ground, and that would create a blind spot in the ground fault detection. Nowadays, the DC side is completely isolated from the AC side, so you don't have that negative to ground connection. The case of the array, the case of the inverter is still grounded, but the DC side is isolated from the AC side. So the metal parts are still grounded, but the DC side is no longer grounded. It's floating. On a floating array, you got to fuse both sides, the negative and the positive. On a negatively grounded array, you only fuse the positive side, but it creates this blind spot in the ground fault detection system. And so if you go research commercial solar fires, back between, say, 2005 and 2000, maybe 12 or 14, they all trace back to this blind spot caused by negatively grounded inverters that had a blind spot in their ground fault detection. Well, none of those articles get into what actually caused the ground fault to begin with. They say, why wasn't it detected? They don't get into what caused it in the first place. And, like the Dietz-Watson fire out in New Jersey, as far as I could tell, it was started by ground faulting in the EMT conduit running across the rooftop, which would be a result of thermal expansion causing the fittings to kind of rub up against the cable in ways they're not supposed to and eat into the cable jacket of the cables inside, and ground fault at that point. So I'm not a big fan of EMT raceways across a rooftop. The ground fault circuit interrupter, a device intended to, detect a ground fault and de-energize that circuit. And then there's a different kind of fault, which is an arc fault. That is, arcing is not a fault to ground. Arcing is a fault within the circuit itself. So imagine you take a cable and you cut it in half. And then you put current through that cable and you butt the two cables up against each other. Now that cable, let's say you're Superman and you're making a super strong bond and that electrons are just going from one cable to the other, and then you pull that cable apart. You're going to get electricity arcing across that gap from cable to cable. So that's going to be an arc fault. Now, an arc fault may be occurring on your system without triggering a problem, because that electricity may be still flowing across that wire. So arc fault detection is more tricky to detect than ground fault. So now the inverters have both. They have ground fault detection built into them. They have arc fault detection built into them. The arc fault detection didn't really come into play until a few years ago. I think NEC 2014 required it. It might have actually been NEC 2011 was saying, hey, it's going to be a requirement, but right now the inverters don't have any, the technology for sensing arc faults wasn't, commercialized at that point. Exposed to harsh winters and humid summers, the seal had broken down and was now providing a hazardous ground path from fault to earth. As a MC4 connector sat in a puddle of water. Maybe. It looked like the fire started in the conduit path to me. And so now we have both the positive side and the negative side fused together. And so how do you mitigate or prevent ground faults versus arc faults? Now, for ground faults and arc faults, avoiding the need for expansion fittings, not having more than 120-foot runs and kind of EMT conduit. Just being wary of negatively grounded inverters. as opposed to floating inverters. How do you prevent arc faults? Make sure all your connections are tight. Using torque wrenches on your connections to make sure that you're within spec. Avoiding the use of fine stranded conductors like welding cable, where you get way more strands than traditionally stranded cable. It says wiring on buildings shall be permitted using metal clad cable, utility feeder cable, mineral cable. You can put it in metal conduit, IMC conduit, cable trays, cable bus, EMT conduit, flexible metal conduit, liquid tight flexible metal conduit. And liquid tight non-metallic conduit. And rigid polyvinyl chloride PVC conduit. And so PVC conduit is a valid raceway up on a rooftop. I know it's ugly, but I think it's a better selection than metal conduit on the roof. Now, inside a building, when we get to section 690 tomorrow, inside a building, metal conduit is required. But up on the rooftop, I guess they say that PVC degrades with direct exposure to sunlight, which is why you would locate it underneath the array rather than to the side of the array. So it gets, shade. So where outside branch circuits and feeders leave or enter the building, there's additional requirements that we're not there to yet. For this conduit, it needs to be supported. A good rule of thumb is every 10 feet, you need a conduit support block. They're not cheap. And then you get into clearance over buildings, which will range up to 18 feet. And so, one idea is, hey, can we put solar covered awnings and solar covered patios, on the top of a roof? Well, not really. You need a 8-foot clearance of overhead power lines on top of the roof, but when that roof is subject to pedestrian traffic, it needs to go up even higher. And so an inspector, if you want to put a solar gazebo on top of a building, I think it has to be something like 16 feet high, which your wind load is going to kill that. The closest you can get to running power cables near windows, doors, balconies, and ladders is 3 feet. Now, you don't want anyone to be able to stick their arm out the window and be able to latch on to that power line. The only exception is at the very top of the building, at that very top window, you can run the power cables along the very top. So you can get closer than 3 feet to your windows when you're at the very top of the building, running on the side of the building at the very top, right above that window. So as we start to get into more specific case uses for like mechanical protection, it keeps punting the requirements to further back into code, where the further we get into code, the more specific it gets. So now we have the raceway requirement, where the raceway shall be arranged to drain and shall be suitable for use in wet locations. There's a raceway seal, where a raceway enters a building or structure from the underground it should be sealed. Why is that? The main reason is for the same reason that underground raceways entering a building or structure should be sealed, you should also go and seal your raceways that go into the building up onto the roof. Because the issue is the temperature differential between underground and the inside of the building, or between the inside building and the top of the roof. Just that temperature condition alone can cause humidity inside that pipe to condense, and now you get water running down your pipe into your electrical systems. That's a very common exam question on is if you have a conductor, a raceway running through a refrigerated room to a non-refrigerated room, what do you need to do? And the answer is to seal that transition so that just the temperature differential alone doesn't create a problem or a leak. All right. A building or structure that is served by a branch circuit or feeder on the load side of a disconnecting means shall only be supplied by one feeder or branch circuit unless, then we get into special conditions such as a emergency power system. So you can only have one connection to the grid, but you can still have your backup generator. You can still have a parallel power production system like a solar array. You just can't have multiple grid connections coming into the same building unless there's our space constraint requirements, or it's a very large building. So if I have a giant warehouse, the power company says your load's going to be over 2 kilowatts or 2 megawatts. It's going to be larger than that. They may establish multiple supplies to the same load. Okay, well, if we only have one utility connection coming into a building, but it's like a multi-tenant building, well, then what? We're going to need to take that one connection and then distribute it across multiple service panels. It's kind of analogous to if you have one service panel and you have multiple branch circuits on that service panel and you have multiple breakers coming off. It's a similar issue. And so how can you slice and dice an electrical connection with breakers? Do you have to have one switch that turns everything on and off, or can you have multiple switches? We're going to talk about that in a minute. We need to define disconnecting means. It says a means should be provided for disconnecting all ungrounded conductors. So not the neutral, but the power lines. Not the thing that's tied into ground, but the thing that's actual supplying the building with power, the hot conductors. You have to have a means for disconnecting that. And that needs to be readily accessible. So this is what kind of trips some inspectors up. They want an external disconnect switch for your solar array. And they say, well, it has to be readily accessible. Well, readily accessible can be, it says at the nearest point of entrance of the conductors to the building, but it also says it can be inside or outside the building. And so if you have power lines going into a building and you have your service panel right inside the wall, that's a readily accessible service disconnect. Someone can pull up to that building, see the power lines going into the building, and they assume that the service panel is going to be, right where the power lines go into the building on the inside of the building. You don't have to have external service panels for a building. The reason why they want disconnect switches on solar arrays to be outside the building is not because of readily accessibility. It's because they don't want to go inside the building. They say, well, we don't have to. We want, if we're working on power lines in the area and we want to shut down all the local power generators, we don't want to have to knock on your door and get access to the inside of the building to do that. That is not a code requirement. That is an AHJ requirement. That's an authority having jurisdiction requirement. And so there's a difference between accessibility and readily accessibility. Readily accessible is a little bit more accessible than accessible. So close approach is accessible, capable of being reached quickly without requiring anyone to climb over any obstacles, is readily accessible. So you go through a door on the other side of the door, not, not closed off. The problem with readily accessible disconnects, though, is that anyone can approach those disconnect switches in a readily accessible fashion. And so the number one most dangerous mistake you make on a renewable energy system is not locking the disconnect switch. Because the grid side of that switch is always going to be hot. We're doing a interconnection right now where we're wiring the utility side up to the disconnect switch, and we have to have our load side already wired up to that disconnect switch, because once the utility side lands on it, that utility side is the only way to power it down is to power the whole building down. And so by all these local jurisdictions requiring readily accessible disconnect switches on the outsides of buildings, they're effectively requiring, the most dangerous point in the whole system to be in a location where anyone can just walk up to it, open up the disconnect switch, stick their hand in, and electrocute themselves. And so it's a very commonly overlooked item, is a physical lock to secure the faceplate of that disconnect switch shut. So I was doing a design where the authority having jurisdiction was wanting a external disconnect switch located at a barn, and we already had a disconnect switch at the side of the road where the service panel was. And they say, well, the solar array is off by that barn, and so we want it at the barn too. Well, the barn was 50 feet from the road. And so, we were saying, well, code says, if your disconnect switch is within sight, then you wouldn't need two disconnect switches. The main one and then the one off where the solar array is. The idea being is that if you're working on the solar array, you'll be able to look at the disconnect switch and see it, and see that it's in the off position. Actually, when we're talking about a readily accessible disconnect switch, that is the main service panel. The breaker that your solar array lands on your service panel, if the service panel is readily accessible and there's a switch on that breaker panel, that is a readily accessible switch where the utility could flick the switch off and then lock the panel board shut, thereby locking you out of your solar array in the off position. Many jurisdictions go a step further beyond code and require it to be a knife switch disconnect, although some utilities are backing away from requiring that readily accessible knife switch on residential systems by recognizing that it's creating more safety hazards than it's solving. Okay, so here's something that was kind of confusing to me. When I got into electrical design, what I noticed is that there's some service panels that have just breaker slots on them. These are called main lug only service panels. And then we had service panels that had a main breaker switch at the top with individual spaces for breakers. So when can you use a service panel that does not have a main breaker switch? And when can you use a service panel, and when do you have to use a service panel that does? This is a common test question. It's called the 6-handle rule. That says within a single enclosure, you should be able to completely de-energize that system by flicking no more than 6 switches. And so if I'm doing a solar array and I'm tying 6 inverters into a single panel, I don't need a main disconnect switch or a main knife switch unless the local authority requires it. If I have 7 inverters on 7 switches, that's when I need this main disconnect switch. And so like on a residential service panel where you have tons of breakers, you're going to need that main disconnect switch. But if you're doing like a utility power distribution panel where you might be landing the supply from the grid on a switch and then the inverter on another switch, and then maybe some exterior power outlets on another switch, and then maybe another inverter on a switch, and a battery on a switch. If you have no more than 6 breakers on a service panel, you do not need a main breaker on that service panel. It's just a little bit cheaper. Now, all these disconnects need to be grouped together. Now, this is something that's interesting. It says, well, if you have a special case, and that would include a solar disconnect, that would be a generator, like a backup power generator, that those disconnecting means need to be remote from your normal disconnecting means. Well, why is that? Well, let's say you're at a hospital and there's a fire that breaks out. The power company wants to be able to show up and de-energize your building, but they don't want to turn off the emergency power system while they're doing that. They don't want to take everyone off life support. They want to power down everything except the life support systems. And so they want to make sure that they know what they're doing when they're powering down those backup power systems. So your special case disconnects need to be grouped separately from your main disconnects. That might mean that your Yeah, I don't think that's given enough thought, because if you're doing a backup power system, usually it's going to be put on a critical load panel. That's going to be separated from your main load. If you're trying to put your generator or your solar backup on your solar array on a battery and provide backup power to the home, you may want to move that disconnect switch to be, a few feet away from your main service panel, so that when you're de-energizing your building, you don't accidentally de-energize, a backup power system that's not supposed to be powered down.